Howdy folks, welcome back to CS 128 Honors. This is Lecture 7, and today we're going to be covering borrowing and slices in Rust. So today we're going to be answering some of your questions that you guys have been asking in the Prior Learn sections, so please keep doing that. We'll continue to address those questions in future lectures. Then we're going to review ownership and borrowing, and finally cover slices of strings and vectors, which again ties into some borrowing. So before we begin, a couple reminders. Homework 5 releases tonight, and it's going to be due in a week at midnight. Homework 4 is due next Thursday on the 22nd, also at midnight. MP1 is due on the 28th, also at midnight. And this is the big one. So from now on, we've decided you can work on homeworks in groups of up to 3 people. So if you work in a group, put a comment at the top of your code submission file with the net IDs of your partners, so we know that similar solutions are working in a group together. And finally, all of your partners must submit an assignment on PriorLearn, so everyone must have the submission in order to get a grade for it. And once again, put that little comment with your net IDs at the top of the file. And then feel free to use the team building channel in Discord to form your groups. Okay, with that, let's get into it. So first questions, go over ampersand string and string, since that was primarily the topic of focus in homework 1, homework 2, and a little bit in MP0. Well, this entire lecture is going to be talking about the difference between those two. But before I talk about that, I just want to say this one's on us. It is somewhat difficult to grasp the differences between the two without knowing ownership, but we definitely should have introduced the API of the two sooner and showed you how to convert between the two and how to work with them. So again, I apologize, this one's on us, but without further ado, this lecture will be covering that difference. Okay. So before I start, I just want to point out this little image on the right. Let me hide my camera here. So you might see this when you take a data structures class. You might have seen this if you've taken something low level that works with C++. Essentially, this is what memory looks like. This is what your RAM looks like when you load up a program. So you have what's known as a stack. All of these like little local variables are stored on the stack, and then you have the heap. The heap is where you put all of the data of unknown size, all of the large allocations of data, that goes on the heap. But then there's these two sections down here, the uninitialized data, so your global variables that are not initialized yet, or initialized data, global variables that have been initialized to a value, and your text section. So your text section is all of the literals built in to your program. So a literal is quite literally this string hello world. Yes, we have a reference that points to this hello world and ref. And in this case, string owns this data testing 1, 2, 3. But anytime you see in quotes some string, that is actually hard coded into your program's data. And I'll show you what that looks like in just a little bit. But with that being said, now we can cover what ampersand str is and string. So string is this little struct. It has ownership of the characters inside it. So this variable string, that's some reference here on the stack, but the actual string data, the characters inside it, those are potentially on the heap. We don't know the size of this array. The string could be 1 character, 2 characters, 1,000,000 characters long. We don't know how big it is, so we're going to put it on the heap. Data that we don't know the size of. But the struct itself, that just contains maybe the length, maybe that array, that's stored on the stack. And then we have this ampersand string. So ampersand string is a reference to a string literal. It's just a reference, so it refers to some memory. An ampersand str is a slice of that string. It refers to some memory of some length in the string. So this reference, well, it refers to this string literal here, we could take a borrow of this string variable, and that would refer to the string data here. And we'll keep going through examples of what this looks like in a bit. Okay, so borrowing and owning is very confusing. Yes, that is the whole idea of learning Rust. Borrowing and ownership is very confusing, and that is part of the learning curve to the Rust programming language. So everything from now on out will be taught through the lens of ownership. So that's going to be structs, multi-threading, functional programming, iterators. Everything we're going to teach about is going to have some little examples of how ownership ties into that. So I hope that you'll just keep getting more and more exposure to borrowing ownership, and hopefully by the time final products roll around, you'll be a little bit more comfortable with that. Okay. So now I, again, want to review ownership because it's going to tie in to &str and string. So the 3 rules of ownership: each value in Rust has a variable called its owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. And we'll pull up this example again. You have this string s owns this data here, and you enter a new block of scope. W owns this string here. We can do something with w, and once w goes out of scope, this data is dropped. It's freed from the heap, in essence. And then when the program finishes, s goes out of scope, and s is dropped. Okay. And then going back to ownership, each variable is the owner, so x owns this data, but there can only be one owner of some piece of data at a time. So in this line here, let y equals x, we're moving ownership of this hello data from x into y, so we're not able to use x anymore, but we are able to use y. And then borrowing and references, so an ampersand represents a reference. You can refer to some value without taking ownership of it. And so when you're creating a reference, you're borrowing some data. And then so at any given time, you can have either one mutable reference using &mut, or an infinite number of immutable references using ampersand. So in this example, we have this string x. X owns this hello data, and we're creating a mutable reference to x. And since we can only have one mutable reference, this line here won't compile. We're not allowed to modify x because y is the only mutable reference allowed to modify x so far. So y would have to go out of scope before this line would compile. Okay, so I want to come back to this diagram here because I'm going to be referring back to it more and more throughout the rest of this lecture. So like I mentioned, this uninitialized data is global variables that are not initialized yet. Initialized data is global variables that are initialized. They have some value when your program is built. And then the text data are all the literals built into your program. So text is the string literals, like the literal quotation marks and then all the characters in between them you see in your program. That is in the text section. So I'm going to briefly show you what a Rust program looks like under the hood. So I have this super basic program. It just defines a variable, and then the variable goes out of scope. So what I'm going to do is compile it, build that program, and then call this command called object dump. So what this is going to do is it's going to look at the program and then format it in a human readable way, and then put it in this file called program dump. So you'll see that there's this contents of section text. This is that text section that I was talking about, and these are the characters that are located there. These are all the string literals that you'll see. And so if we search for this string, we're going to be able to find it in that text section. So search for some random, there we go. In the text section, we have this built-in string literal, like hard-coded into the program data. So this is something hard-coded into my program in memory, and this variable ABC is a reference to this hard-coded data. So there isn't really any ownership of this data. Well, the program owns this data. It's in the program stack, or rather in the program's memory, and ABC is simply a reference to that data. So there is no overt variable ownership here, but ABC is a reference to something in memory. So that's the biggest thing I wanted to show you. This string literal is hard-coded into the program. Oops. And ABC refers to this string in memory. Okay. Hopefully that makes sense. If it does not, please ask some questions in the Discord, and I'll be happy to explain it further. Okay. So once again, I'll be referring to this diagram throughout the lecture. Okay, so we know from the rules of ownership that a string has ownership of the characters in that string, right? But if we wanted to get a substring efficiently, we would like to be able to get some type of reference to a portion of the string, a substring, and we want it to be a reference so we can avoid having to copy over that data. Maybe our substring is really long, maybe it only excludes 2 characters of the original string, which is 1,000,000 characters long. We want to avoid having to copy over all of that. So we want this substring to be a reference. And we also want the original string to keep ownership of its characters. We want to be able to have this substring and take future substrings of the original string, so the original string needs to keep ownership. So let's say we have this string, s1 owns the characters of hello. Well, under the hood, we might have this capital S string. It has a pointer to some characters that it owns, so HELLO. We know its length is 5, and this capacity implementation, well, this is for sort of adding and appending the strings and making it more efficient. So don't worry too much about that. But this is probably what a string would look like under the hood. And we want to be able to take some reference to a subset of these characters. So let's just say HE. We want to be able to refer to some substring while S1 keeps ownership of those characters. So we need an efficient way to take substrings. So enter string slices. So again, strings have ownership of their characters. So if we wanted to get a substring, we can just take a slice. So a string slice is a reference to just a portion of a string. And this reference can be some substring or the entire string. It's just a reference. It's a pointer to some memory and the length of how long we want this reference to be for. So 2 characters, 5 characters, 10 bytes, 20 bytes, whatever it is, some memory and some length. And so this way the original string has ownership of the characters. S keeps ownership of this hello world data, and we have these variables that refer to S. So to take a string slice, you borrow your original string, and then you tell Rust how far you want to go, starting from where. So if we wanted to have this hello string slice that just refers to the first 5 characters of the string, we'd say start from index 0 and go to index 5 and exclude the last index. So this substring would be just hello. And the same thing applies for world. Start at index 6 and go all the way through index 11. And I'll go more about the sort of syntax here. You'll notice that omitting the starting index is equivalent to 0, and omitting the last index is equivalent to the string length. I'll go over this in the next couple slides. And like I said, your substring can be the entire string. So start from the beginning, and at the end, hello world is still a reference to the original S. It doesn't own anything. It is simply a reference to the string data. Okay. So like I mentioned, you use the ampersand to create a reference, and then you specify a range. So the range can follow the pattern start ... stop. So start at the inclusive start index and stop at stop, which is exclusive. You can omit the 0, and that'll tell Rust to begin at index 0. Or sorry, you can omit the start. You can omit the end, and Rust will know to stop at the end. Or you can drop the start and stop indexes altogether, and Rust will know start at index 0 and go all the way to the end. So I should note, slices are read-only. They're immutable references. And this should be fairly straightforward because you're creating an immutable reference to that string. So we're not able to change the original data of S because we're taking substrings, because we're taking immutable references. And we don't necessarily want that to happen because, say, we want to take multiple substrings. Well, back to the rules of ownership, there can only be one mutable reference at a time. So Rust enforces that substrings or slices are immutable. Okay. So I touched on this earlier, but I want to go over what string slices look like under the hood. So let's say I have this string s, which is hello world. It owns all of these characters here. And then we have the length of the string 11 and the capacity. Well, under the hood of a string slice would simply be a pointer, so a valid reference to some data, and then the length of how far we want to go. So when you have this notation 6.11, Rust knows 11 minus 6, that's the length of your reference. So we have a pointer to the start, and then the length of how far we want to go, and that's your reference. Just some subsection of memory. Okay. So I covered this earlier, but I want to go over it again just to reiterate. You have this string literal world that's in your text section. We saw that with the random string that we found in the programmed data. And then world is simply a reference to that. It's a pointer to somewhere in memory, and then a length of how far to go. So when you say let world is an ampersand string equal to that, world is hard-coded in your program, and the variable world is a pointer plus some length of how far to go. Okay, and then back to this hello world example, s is, has some string, and then it's a pointer to some data. This data, we don't necessarily know the size. It's an array of some unknown length. That would be on the heap. And then we have this string reference. This is a pointer to somewhere in memory. So this world pointer actually points to somewhere on the heap because it points to the string data of s, and it's just a length. Okay. Let's go over a quick example of how to use string slices. Okay. So you've seen this example before. Dropping the start index is the same as putting a 0 here, and dropping the end index is the same thing as putting the length there. And I should note you can put variables here. They don't have to be literals, so this also works. And we'll run this. There we go. So the first string reference, start at 0, go to the end of hello. Second one, world, start at 6, go all the way to the length. The length is exclusive, or rather the end is exclusive, so we're not trying to get any indexes out of bounds. And finally, we can take a reference to the entire string. So from 0 all the way to the end, that's what Rust interprets this empty range as. And then, okay, so I want to point out, this is somewhat different than simply borrowing. So if we have a string slice that goes the entire string, that is still just a pointer plus some length. But if we were to actually take a borrow, so just ampersand s, that's fundamentally different because a borrow of some type is a reference to that type. So ampersand s is a reference to the string, but a substring is a reference to some memory. So a pointer to the memory and how long to go. So same principle, just a little bit of a nuance. Okay. So you can also take slices of vectors. If you think about it, strings are just vectors of characters. So extending that idea to vectors of any type might work, or it does work. So vector slices are constructed the same way as a string slice. You borrow the original vector with an ampersand, and then you specify a range with the start ... stop notation. Same rules apply. You can drop the start index, you can drop the end index. Both work. And again, slices are read-only. The vector retains ownership of the data that it contains, And we want to be able to take multiple slices. So slices have to be read-only. And you might notice if you type this in an editor, vector slices have type ampersand and then an array of t. So this is similar to ampersand str. You have your ampersand at the beginning, but vectors are in essence an array, and then they contain data types of type t. This is known as a generic. You might come across these in C++, in Java. We'll be going over these in lecture 10, I believe. This just means that the vector can have elements of any type. And t is just a variable to represent that. So your vector slices are a reference to some array, so a reference plus some length. And a borrow to an array is, well, vectors just have arrays under the hood, so a borrow to an array makes sense. Okay, let's go over a quick example of this. So I have my vector here, v. v has 128, 199, and I am taking a slice at the start. So a slice of starting at 0, and then going to index 3. Index 3 is exclusive. So this first slice should just be 128. Let's just comment out these two examples briefly. Okay, there we go. So the first 3 numbers that are printed out, all the numbers in my slice are just 1, 2, 3. And notice you can use for loops on string slices. You're simply iterating over an array, so for each value in my slice, and you'll notice that each value is a reference to the original data. So everything is references with slices. Okay, let's comment out this second example, or uncomment out. So this second example is a slice from index 2 to index 5. So start at 8 and then go all the way up to index 5 exclusive. So 8, 1, 9, and then skip this index. And there we have it. We print out 819 and stop there. And finally, we can take multiple references to our subarrays. So let's say we want to construct subarrays of size 3. So that would be 128, and then 281, and 819, and finally 199. So we start at some start index and go through the length -2, just so we don't have any index out of bounds issues. We take a slice, starting at the start index and going to the start index +3. Remember, we exclude the last one, so our slices will be of length 3, and we print those out. And there we have it. We have the first slice, 128, then 281, then 819, and finally 199. All right, folks, that's it for today. Somewhat short. I hope all of this makes sense. Please keep asking questions in PrairLearn, ask questions in Discord. We'd love to explain things to you. And yeah, take care.